Good evening, ladies and gentlemen, and welcome to the Space Telescope Public Lecture Series. It is my pleasure to be your host. I'm Dr. Frank Summers of the Office of Public Outreach. And when you came in, hopefully you picked up one of our pretty pictures. This is a brand new pretty picture, one that we haven't given out before. It is the Southern Crab Nebula, which I don't guess you could see a crab there. I see more of a tick, to be honest with you. But you know, this is a special image. This was one that we released for Hubble's 29th anniversary, and you'll see on the back that it's not a full color image. It's actually composed of several spectral lines put together. Okay. So these are the spectral lines that were used to put it together. So it's not how it would look to the human eye. It's how it looks in these specific spectral lines that Hubble observed. And of course, astronomers use these spectral lines to pull out different physical characteristics of the object under study. And I'm assuming that the text on the back tells you all about that. If you didn't get one, there are some extra you can get on your way out. Please silence your electronics. Actually, I know I did not silence my electronics, and that would be embarrassing. So airplane mode, there we go. Okay, let's see, what else? Tonight, yes, we have the Astronomer's Toolkit. This is going to be an interesting talk. It's a different kind of talk than we usually give. We usually talk about all this science stuff and everything right here. But we also have these wonderful talks about how we create science, and Brandon's going to do some stuff with, hopefully, a live demo. Yep, live demo here. Okay, he's going to walk the tightrope. Let's see. Next month, we have black holes and gravitational waves, always a very popular topic from Emmanuel Berti across the street at Johns Hopkins. November, we have our infamous TBA, who appears every now and then, but always cancels before it's time for TBA to give the talk, which means I will have somebody filled in that slot. You never try and ask people to commit to talks in August over summer break. Right, so now it's September, I can get their attention, and I'll be able to fill that one in. In December, we have a very long title, Red and Brown Dwarfs, Understanding Our Smallest and Closest Substellar Neighbors. Okay, this is understanding the stars around us that happen to be relatively small stars. Okay, all right. If you would like to know all about that, you can go to our website. And if you remember, we changed our website over the summer. We are now holding it. We're not hosting it mainly on. It's still on Hubble site, but our prime hosting site for it is now stsci.edu, and we have the nice shortened public-lectures. All right, something even I can remember. Okay, so. So here is our website for the public lecture series, and we have the links to the webcasts here. We have the sign up for the email stuff here. We have information across here. We also have, if you scroll down, because these are now optimized for phones, all the websites are now optimized for looking at it on your phone these days, so you got to do lots of scrolling. But you get down and you can see, of course, our upcoming lectures, as well as below that, we have a complete listing of the past lectures. Plus, we improve the individual lecture pages so that we have full information on them. We have links to the, whoops, wrong one. There we go. Links to the STSCI webcast here, links to the YouTube webcast down here. Okay, and I know that's semi-gratuitous use of this little spotlight feature, but the folks on the online webcast cannot see my laser pointer if I use that, so that's why I'm using the special spotlight feature here. All right, okay, email the announcements. You can sign up on our website, or just if you want to write it down and hand it to me at the end of the lecture, I can put you in there. You only get 2 or 3 messages per month. If you have comments or questions, publiclecture@stsci.edu. If you'd like to follow us on social media, especially those of you on the webcast, we have Facebook, Twitter, YouTube, and Instagram. Myself, I sometimes am on Facebook or Twitter, although I will admit I took the entire month of August off from social media. It was actually kind of refreshing. I'll be back now that the fall has hit. Tonight we also have the observatory. The weather is very much permitting. It looks very clear outside. So after the lecture, the Maryland Space Grant Observatory staff, I'll have everybody meet down here, and they can take some people across the street to do the observing. Also, if you can't make it tonight or you want to come some other time, md.spacegrant.org. They have the observatory status on there every Friday evening by 5 or 6 p.m. They will post whether or not they're going to be open that evening, and you can go do it then. All right? Now, our news from the universe for September 2019. And I only have one story for you tonight, and they are eye-dropping images of Jupiter. Okay? So we take pictures of Jupiter when it's at conjunction, okay? And we got another really good one just a few days ago, okay? This is our image of Jupiter at conjunction this year. And it's really, like Jupiter always is, it's gorgeous. Although, you look at it and you go, all right, well, Hubble's taken pictures of Jupiter since the 1990s, okay? I mean, what's here that we haven't seen already? Well, we've seen it so many times, but that's actually the point, is that Hubble can observe it year after year after year, okay? So look at the 2019, okay? Here is our 2014 image, all right? And if I blink back and forth, I go here, and I go here, they don't look all that different, right? But by tracking it over the years, we can see that the great red spot on Jupiter is shrinking. So here is a picture, whoops, sorry. Here's a picture from 1995 up here, and then 2009 and 2014. And when you compare them, you can see that the great red spot is actually shrinking. It's getting smaller. At one time, it was estimated to be 3 times the size of our planet. And now it's down to about 1 time the size of our planet, okay? So by looking over the course of long numbers of years, we can see that. We can also see other changes. So we follow these white ovals, these smaller storms. And from 97, there were these 3, FA, DE, and BC. In 98, DE and BC combined to make BE. And in 2000, FA and BE combined to make BA. Oval BA, 3 white storms that combined to form oval BA in 2000. And then a few years later, that oval turned red and became red spot junior. We saw for the first time ever the formation of a red spot. So we're getting to see changes like this, okay? And that is why this latest image is not just some random image that we do, but it's part of a very dedicated program. And that program is called OPAL, the Outer Planets Atmospheres Legacy Program. Because this is one of the things Hubble really can do, is look at these planets for years upon years and follow the transitions. So this is what Jupiter looked like. This is a full global map of Jupiter taken by Hubble in 2015 by the OPAL program, okay? And then this is what it looks like in 2019. All right, and we go back and forth, 2015, 2019. You'll notice that this central band along here, look at that color along the central band, that orangish color there. If I go back, it's more of a whitish color. One of the things they noted in this year's image was that the aerosols at higher altitude along the equatorial belt seem to be activated, and you're getting a bit of a more orange color. We're also noting that, yes, the great red spot has continued to shrink. Okay, so that is a small great red spot. It's only the size of our entire planet, okay? That's that small. But what do you notice even more, you notice that red spot junior is no longer red. Red, we saw the first time the formation of a red spot, and now our red spot has dropped out and has become a white oval again. So when I said these were eye-dropping images, I actually was talking about somebody's been using eye drops on Jupiter because we all know that it gets the red out, okay? I wish it were that easy of an explanation, okay? We're losing the great red spot. The red spot junior has gone away, and we do not know for sure why, okay? We do not know why we're losing the red in Jupiter, all right? But that's why we're doing this OPAL program, so that we'll have the data to study these effects and then make better and better hypotheses, all right? I'm going to leave you with one final image that's not Hubble, but oh, is it just gorgeous. This is from the Juno mission in 2017. It's a close-up of one of those white ovals. And look at all the hydrodynamics going on in here, okay? This is the kind of stuff I just love, okay? Those beautiful natural swirls that come about in Jupiter's atmosphere are just amazing. So I don't use this to, well, first of all, to show you that it's really gorgeous, because I love it, but also to remind you that you need those missions that go to the planets to see these great details. But they can only be there for a few years. We've got Galileo, we had Galileo, Juno is there now. We have these missions that can go to the planets for a few years, but the value of Hubble is that it's been up there for 29 years now, and it can see the longer term effects. You can get the details with the space missions, you can get the long-term effects over decades with the Hubble Space Telescope, okay? All right. And now we move to our featured speaker. We are very happy to have here tonight Dr. Brandon Lawton. He is an astrophysicist in the Office of Public Outreach, whose research, if you guys remember, he has come here and talked about, studies dust in galaxies. The dust clouds are incredibly important because they're from which the stuff from which stars actually form. I mean, it's dark, invisible light, so people don't pay as much attention to it. But when we have Brandon around, he always makes sure we remember that the dust is really the most important stuff. All right? However, he is an astronomer in the Office of Public Outreach. And in that process, we do a tremendous number of activities with students, with teachers, with the general public, in which we explain how astronomers learn what we learn. And he decided the last time I chatted with him to do this, he decided, all right, I'm going to take that and show off the Astronomer's Toolkit. So ladies and gentlemen, Dr. Brandon Lawton.
Thank you, Frank. Which one are you?
Which one is this one?
It's number what?
Thank you, Brad. Thank you. Got a fan club in here.
That should be one.
Okay, now we have to. That was some of my dust you saw there. That was, yes. All right, thank you so much, Frank. All right, so I started here, like Frank said, about 10 years ago. I was a postdoctoral researcher here working in dust. Now I work in the Office of Public Outreach since about 2011. And we're going to talk a little bit about the Astronomer's Toolkit. This is going to be a little bit of a whirlwind, I admit, because astronomers have lots of tools, as all scientists, all engineers do, right? But I want to also show you some things that you can take back with you that you can do on your own. All right, let's go to the next. First, a little bit more about me. So I grew up in Washington State, and I grew up, and I have a similar sort of story that a lot of astronomers do and scientists do. You look through the telescope for the first time and you see something like Saturn, it sticks with you, right? You just fall in love with the night sky. And my neighbor had this telescope, and I saw Saturn through it, and I was stuck. And then my parents, growing up in Washington, we didn't do a lot of trips around the country, but we did save up because I really wanted to go to the Kennedy Space Center as a kid. So we went there, and that was an amazing trip, and it meant a lot to me. And really, my love for astronomy was born quite early. But it wasn't really until I was an undergraduate at the University of Washington, which is that middle picture there, where I really got to do sort of the participatory sport that is science, that is astronomy. Okay, you can, really the best way to learn and the best way to appreciate anything is really to get in there and try to do some of it. You're going to make a lot of mistakes. I certainly did, but it's a lot of fun. And so what I was able to do is at this Monastash Ridge Observatory in the mountains of the Cascade Mountains in Washington State, I got to spend entire summers up there basically by myself, just taking images of the night sky. I was lucky to work on a research project with Professor Paula Scotti there and Professor Chris Stubbs on variable stars, and I'll talk a little bit about variable stars later in this talk. But I gotta do what's called differential photometry, and I'll explain what that means later, on these stars that vary over the course of the night. And it's a lot of fun to just be out there and doing science. And then I took that to my graduate work in New Mexico. That's the far right. You can see the big telescope on the lower right is a 3.5 meter telescope at Apache Point Observatory. And that's where I fell in love with dust. It's very dusty in the Southwest, so it makes a lot of sense. But I did a lot of research on dust, and I did research on some very enigmatic, mysterious things, which I'll talk about as well in this talk. Okay, so let's go ahead and move on. I think a little history, though, to set the stage, right? Because we have this toolkit, but science is always built on the people that have come before us. And humans have had observatories for thousands of years. Okay, so on the left, there's an observatory in Portugal. It's about 6,000 years old, and it was actually partly a crypt as well, but it's an observatory, and the hypothesis for this observatory is that it allowed the people, the nomads of the time in Portugal, to go inside there and look out that viewing window to see stars before the sun had set. And they would look for stars that would signal the change of the season, so they knew when to go to the mountains with their herds or whatever they were doing. So they really needed that interior cavern of rocks there to block out the sun so they could see the earliest point at which those stars, in this case I think it's Aldebaran, but the stars as they were coming up that signified spring or fall or what have you. So, and of course we all know that there are sundials, and the Egyptians and cultures across the world have had observatories where people have observed the night sky, looked at the positions of the stars, and so on. So this is really a human endeavor that's gone on for thousands of years. Fast forward many thousands of years to just about 400 years ago, and you have a picture there, painting of Tycho Brahe in the late 1500s, who we didn't have telescopes yet, right? That wasn't in our toolkit. But what he had was he had an observatory, and he had helped perfect some of the instruments of measuring very precise angles of the sky. So, for example, sextants and quadrants and things like that, so that he could measure the positions of celestial objects incredibly accurately, as well as have clocks that had the hours and seconds and so on, so he knew exactly when those celestial objects were in that exact part of the sky. And that was incredibly helpful because his assistant, Johann Kepler, used that very detailed information to come up with the Keplerian, basically the Keplerian laws, if you will, that basically told us how the celestial, or how the planets went around the sun. So his positions were incredibly detailed and incredibly valuable for the time, and it really pushed the field of astronomy forward. But of course, the telescope helped us a great deal. So it's probably the most well-known in our toolkit. I'm sure everyone's aware that we use telescopes, right? So here's a painting of Galileo Galilei with a telescope. I think this is when he's showing the Catholic Church his observations. That's what it's portraying there. But this was basically built from the spyglass, which was thought to be invented in 1608. And Galileo took that invention and tried to better it in some ways, and he basically used it then to build a telescope to look up at the night sky. In 1609 is when he did that. Okay, so you can see we're progressing in the toolkit here. We have telescopes now, and now we just jump all the way to Hubble, right? So now we have telescopes where we're not just using lenses like Galileo used for the optics, where the glass lens collects and redirects the light to a focus where your eyeball is so you can see it. But now we have these telescopes on the ground and in space that use mirrors to reflect the light to a focus and sensitive detectors to capture it. Thank goodness we don't need somebody peering through an eyepiece up there in space. That would be very, very painful. So we've really moved along with our technology. So let's talk a little bit about telescopes before we move on. I want to remind you all, and I'm sure many of you are aware of this already, that the light that we see with our eyes makes up a very small part of what's called the electromagnetic spectrum, the light that we can see, right? And that's noted in the middle there, the visible light. There's a whole host of wavelengths or types of light that our eyes cannot see. So those include higher energy light, like gamma rays and X-rays and ultraviolet rays, and lower energy light, like infrared, microwave, and radio, okay? And our toolkit, if we really wanted to understand the universe, our toolkit needs to expand to be able to observe those wavelengths of light. So we needed to build special telescopes that can capture and detect and record those wavelengths. So all these telescopes, NASA has a whole fleet of telescopes up there. A large reason why we have so many telescopes is because we need special technology to observe those different wavelengths. This also shows you why we need to put telescopes in space for many wavelengths, right? So the colored lines show you how far down that wavelength reaches to the surface, okay? So thankfully, gamma rays and X-rays don't make it to the surface. It's a good thing, all right? But if we do, in astronomy, if we do want to understand the highest energy sources in the universe, it means we have to put our telescopes out there above the atmosphere where we can detect it. Visible light does reach it to the surface. We have lots of optical ground-based telescopes, but there's a reason why we would still want to put something like Hubble in space, and it's because our atmosphere acts like a fishbowl, like we're underwater, right? The atmosphere blurs the light as it comes from space. So if you can get above the blurring atmosphere, right, then you have a more clear vision of the universe. And likewise, you can see that, for radio, it's quite lucky you can have a lot of wavelengths reach the ground. I want to point out this is a very interesting NASA mission called SOFIA, where they actually just put a giant telescope in the side of a plane, a jetliner. And they fly that around to get some of the infrared wavelengths. So they open up the entire side of the jetliner and they observe. Okay, so our toolkit has greatly expanded from the early days of Galileo, where he just had his nice refracting telescope, to now a whole suite of telescopes. But of course, telescopes aren't just the lenses and the mirrors. They're also the other things on there that let us record the data, right? So telescopes capture the light, but we need some way to record it. We used to use our eyes. For a while, we used photographic plates, but now we use something called CCDs, charged coupled devices, which were first invented in 1969 by Bell Labs. Now, CCDs are a wonderful invention because they're quite sensitive to light, and you can actually count the photons of light that come in. The way they work is I kind of like to use an analogy where you can pretend like if someone asks you, okay, it's stormy outside, and you want to play a game, you have all these buckets, capture as much rain as you can, what would you do? Okay, you could try to get one big bucket, or you could try to get a bunch of smaller buckets, right? Telescopes are like big light collecting buckets, okay? They collect all those raindrops, but we still need to count those raindrops. The CCD detectors does that for us. CCDs are basically have these little buckets in themselves, these little pixels, and a photon of light will hit that particular pixel and release electrons, and we can count those electrons. So it's like a grid of little traps that basically collect the pixels, and you get images like you see on the right. So this detector here is the ACS detector that's on Hubble. It's over 10 years now, and it captured that image on the right of the Whirlpool galaxy. Now, the ACS detector is 16 megapixels, 16 million pixels in that detector, which is quite amazing given it was over 10 years ago that it was launched on Hubble. Of course, now you can buy a digital camera that has twice that if you want to spend the money. Our phones are getting to the point where they're getting not too far from this, 8, 10, 12 megapixels, okay? So this is an amazing instrument, but the toolkit, if we want to do more, we have to do better. We have to expand our tools. So we have these CCDs, these digital tools. What can we do? Well, I like to think, one of the best examples of what we can do currently with our detectors. This is another ACS. The ACS is that camera I showed you. That stands for Advanced Camera for Surveys. It's on the Hubble Space Telescope. This is over 400 pointings of the Hubble Space Telescope to make this image, this mosaic, of our nearby Andromeda galaxy. And this doesn't do it justice. If you actually download the full image, and you can do this online. If you download the full image, there's over 100 million stars that you can make out in this image. Okay, this is only about a third of the Andromeda galaxy, our nearby galaxy, right? So this is taking our detector technology and stepping across this galaxy and putting it together. And I should also mention that along with detectors, our space telescopes have filters on them. Okay, now, if you want to study an object across all the colors, you might want to use filters to just study one color at a time, and that's what Hubble has, and all these telescopes have these filters. So to make this image, it used multiple filters, and it had essentially red, green, blue filters, essentially. And then you can study them individually to see where the blue objects are, which tend to be, in this case, new forming stars. The red tends to be indications of older stars. You might find dust, the best thing in the universe. But when you have the different filters, right, then you can study the pieces of the galaxy. So filters in combination with these digital detectors allow us to study galaxies in greater detail than we've ever been able to do before. So we're able to piece together essentially the history of our closest neighbor, our closest big galaxy neighbor, the Andromeda galaxy. And so it's an amazing, but let's do better. And we're going to do better in the mid-2020s when WFIRST launches. Okay? WFIRST is the Wide Field Imaging Survey Telescope. Wide Field Infrared Survey Telescope. And its imaging is going to be amazing. So here again is this 411 pointings of Hubble. This is, by the way, a ground-based image of the Andromeda galaxy. And then overlaid is the Hubble 411, much higher resolution. Okay? And then here is the footprint of the detector on the WFIRST telescope, the Wide Field Imager, over 100 times the field of view. Same quality level of data as the Hubble. Okay? So instead of 16 megapixels, we're talking like 288 megapixels camera. Okay? So we're really going to get big images of the sky with this telescope. Okay, so our toolkit is always increasing, but I need to put a caveat that the reason that the toolkit is increasing, or the reason why we're making our tools better, is not because we can, but it's because each generation of telescope or instrument before has given us mysteries that then dictate the kind of technology we need to solve those mysteries. Science is a never-ending exploration. So Hubble and other telescopes have discovered amazing things, but have also led us with a lot of mysteries. And WFIRST is going to be one of those missions that's really designed to understand some of those mysteries. In particular, I should mention the mystery of dark energy and exoplanets. All right. This is one of those little places where I just wanted to take a quick break, and let me see if you can see this, and do an interactive. I wanted to point you to a resource. It's called it's called ViewSpace. Let me see. Okay. All right. Close that. All right. So on ViewSpace, what you can do is you can go and you can actually look at these images. All right. So you can go here and you can, on the front page, there's the whirlpool, which I think this is the whirlpool, or it's the pinwheel, I can't tell. Which you saw an image earlier if it's the whirlpool. You can slide it across, and these are the actual astronomical images. Okay? This is X-ray and visible. But let's do better. This is all free, by the way, this ViewSpace. If you go to the interactives, here's an interactive of what the world, a cartoon of what the world looks like in visible light, infrared, radio, microwave. You can see there are different sources for each of these: ultraviolet, X-ray, and gamma ray. I also want to point out that there's labels here, so you can turn on and see what things are. This is a nice thing to show off if you want to do a quick demonstration, but let's do star formation because it has lots of beautiful dust. So here is visible, right? This gets you an idea of the power of multi-wavelength astronomy and the detectors on all of our telescopes. So this is a visible light with Hubble. If you scroll over to near infrared, this is what Hubble looks like. It has near infrared capability. And you can actually see inside those dust pillars, and you can see stars being born in the dust. If you go to the further into the infrared, that dust actually starts to glow, okay? And I believe this is Herschel Space Telescope with this image. The dust starts to glow because the dust is being heated by stars. So the dust is glowing there. If you go in the other direction, you go to X-ray, what you find are the hot stars that are carving away at that dust. So that if you've recognized this image here, invisible, we sometimes, it's the Eagle Nebula, we sometimes call these the pillars of creation. They're not going to be there forever. In fact, they're being constantly eroded by the hot young stars that were born from that nebula that are releasing all that ionizing flux and eroding it away. And so you can see that in X-ray, and then there's a nice multi-wavelength where you can put the X-ray, visible, and infrared together. Okay. So there's a lot of things you can explore in ViewSpace. I encourage you to check it out. Let's go back to the slide. But this is another one I wanted to show you. This is another interactive. I told you there would be interactives, even though it's really me just interacting. But you know, we should have said, you know, bring your computers. But this is all online as well. So if you see this and you want to go on and explore with this, or you want to share it with others, please do. I want to show you a really cool thing that we just started doing. It's called NASA's Astrophoto Challenges. Basically, what we do is we allow, we have it in the summer, which we just finished, and we'll have another one in the winter, and then another one in the summer, and so on. And what we do is we provide users, we provide anyone the ability with just their computer and an internet connection to go on and to use ground-based telescopes to take their own images. And we provide the free online software with tutorials. It's relatively simple, and I'll walk through an example of it here. For you to put together your own astronomical images, astrophotography, if you will. Okay. We also provide the NASA data, much of the NASA data for those objects. So you can make, you see those beautiful, you know, Frank is always up here at the beginning of every public lecture showing you those beautiful releases that we provide, that Space Telescope produces or NASA produces. You can create your own version of those same objects with the same data. So let me show you what that looks like real quick. So if you go to Astrophoto Challenge, I'm just going to show you, okay, so if you go to Micro Observatory, that's the robotic telescope. You can observe the object and do it yourself. But let's just go to the NASA data one. And I just want to show you how it works. So, and there's a step-by-step guide, but basically what you do is you open up this tool. This is a pared down version of the same tool that astronomers use for their research, by the way. Okay, we pared it down though, and what you can do is on this tool, you go over to images and you say, okay, I really want the Chandra X-ray of the Whirlpool galaxy. Okay, it puts it up there. All right, doesn't seem like much, but if you step through it, there'll be a hint that this is in a linear scale of brightness, and for astronomical images, it tends to help to put it in a log scale. There we go. You can mess with the controls on the side until you can see it better. So you can kind of see it there. You can add color to it. So I want X-ray high energy. I want it to be blue, so I'm going to color it blue. Okay. I'm going to click this RGB mode. Again, this is all on the tutorial, so you can do it. All right. Now let's do Spitzer. Let's look at the dust, because that's what we're really interested in. Yeah. All right. Again, do log. You can look at the dust. I'm going to go ahead and color that red. By the way, I'm doing the typical color scheme that astronomers would use, where high energy is blue, low energy is red. But you can do any color scheme you want. It's all up to you. All right. And then we're going to do a Hubble. Let's do a Hubble green. And we will color it green. And all right. So So there's a Hubble green. Let me see here. There we go. And then you can combine them together, and you get this, and let me zoom out so you can see the whole thing. You get this beautiful, now in this, the red, it explains, there's videos here on what these colors actually mean, but the red is the dust, okay, that's being heated by stars, okay, and that's the Spitzer infrared. The blue is the high energy stuff that's coming from high energy sources like black holes or neutron stars, okay, that's what blue is. And then green, which unfortunately looks like it didn't come through very much on here, but green from Hubble would be the typical stellar population, the normal stars, okay? And so there's other wavelengths in here you can mess with, but it's a fun way of just getting into the astrophotography. And I should mention that I talked about how these detectors are pixelated, right? They're actually pixels. If you zoom in far enough, you can start to see the pixels of the image, okay? Right. All right, so that is what we call NASA's Astrophotography Challenge, and we're coming up with a nice image in the for the winter. I also want to show you, we have images from astronomer, or we have videos from astronomers explaining what the different types of light tell you. And then I also want to show you that from the summer challenge for the Whirlpool Galaxy, we also highlight some really standout entries, okay? We highlight standout entries, and scientists actually provide commentary on why they're so beautiful. So if you also want yourself or anyone you know to take part in this, we'll be doing it through December through January in the winter. You can make your own beautiful images. You can submit it, and we'll highlight the standout entries, and it's something that you can show off to others. Okay? So this is sort of this is a very similar process to how astronomers put together basically images. And I believe Joe DePasquale, he had a talk a few months ago. Yes. So it was probably along these lines about how he puts his images together. Yeah. All right. Okay. All right. Let's go ahead and move along here. All right. All right. I want to talk a little bit about photometry now. All right. So with the digital detectors, it's possible to do what's called photometry, which basically is just counting the photons, counting how many photons hit the detector. And this is a tool and a technique that has been incredibly important in astronomy. I'm highlighting Henrietta Leavitt here. She did groundbreaking work on this at Harvard. In fact, they named a law after her, Leavitt's Law. This is a paper from 1912 that she produced. This is basically looking at those variable stars, which I talked about earlier, stars that vary in the night. And what she noticed is that if you look at a star's period, how much it brightens and fades for certain kinds of stars. If you look at that period and you also measure the brightness changes, okay, there's a relationship there. And that's very important because this was really the first what we call standard candle for astronomy, which means that if we can measure the period, which is a pretty simple measurement, you just measure the period of a star getting brighter and fainter. If you can measure that period, you can just use this chart to calculate how bright it really is. Its intrinsic luminosity, how bright it is, right? That's like if someone handed you a light bulb and you didn't know how bright it was and they told you it's 60 watts. Okay, well now you know something, right? So we now know, these are called Cepheid variables. We now know how bright they can be if we look at their periods. This is an incredibly important discovery, and here's why. At the time, in between 1912 to 1920 or so, there's this, and even earlier, there's this big debate in astronomy about these nebulae that they saw in the universe. Were they inside of our own Milky Way galaxy, or did they exist outside of our Milky Way galaxy? This is called the Great Debate. Okay, and the Great Debate was essentially a debate that was held in 1920, almost 100 years ago. And there was there were two astronomers going back and forth, and they couldn't resolve it. But lo and behold, Edwin Hubble using Henrietta Leavitt's discovery of being able to calculate the brightness of a Cepheid variable, took observations of a Cepheid variable from and around the Andromeda Nebulae, he called it, Andromeda Nebulae, which we now know to be the Andromeda Galaxy. And he calculated its intrinsic brightness. And if you know how bright it should be, and you know how bright it appears to you, you know how far away it is, okay? And he was able to determine that Andromeda was actually way outside of our galaxy. And that broke the great debate. That basically answered it to us, where the Milky Way wasn't the entire universe. All these galaxies were outside of our universe. I mean, outside of our galaxy. All these other galaxies were outside of our own galaxy. The universe was a much bigger place than we had thought before. All right, so today, what does that mean? Well, we're still using this tool, this technique. We're still using this photometry and watching these variable stars. And in fact, you may have heard a lot of press over the last 6 months or so over this new debate over the Hubble constant, the expansion of the universe, okay? And so using this tool and technique, astronomers using the Hubble Space Telescope observed a lot of Cepheid variables, which this is supposed to represent a blow-up of Cepheid variables around the Magellanic Clouds. And they observed these Cepheid variables, and they came to a very, they observed the Cepheid variables, and they were able to come up to a very good estimation of how fast the universe is expanding by looking at those Cepheid variables, okay? Okay, so these are a standard candle, and you can use them as a distance ladder to understand how fast the universe is expanding with time. The problem is that it significantly differs from the result of another space telescope called Planck that looks at the early universe, looks at the conditions of the early universe, 12, 13 billion years ago. We think we understand the physics from since then. If you just play the movie forward, the expansion rate at the current time should be x, but their x doesn't match their value. Basically, there's a discrepancy between what they think the expansion rate of the universe is right now and what it currently is. And this is turning out to be actually a modern day debate that's turning into a big thing because they've gotten their errors down quite small, and they think that there may be new physics here, okay? So I want to point this out to you because these tools and techniques that were, first really started from Henrietta Leavitt and the computers at Harvard back in the early 1900s, those techniques are still being perfected and used today to find new clues to the physics of our universe in the present day. Of course, now we have Hubble, so that's a big help. All right. Okay. This idea of photometry is also used to find alien worlds around other stars, exoplanets. Okay. So you can use this same technique. Let me see. This is what the Kepler Space Telescope did. Kepler was launched in 2009, I believe, and it stared at a blank patch of sky, or not a blank, it stared at this patch of sky, definitely not blank. There's a lot of stars in this patch of sky, but it stared at it for many years, and it just looked for the dimming of, basically the photometry, the dimming of the star, of all those stars over time. And it looked at about 150,000 stars, looked for the dimming, and if the dimming kept repeating, they could infer that perhaps there is a planet going around the star and in our line of sight blocking that star. Okay, so this is called the transit technique, but really it's basically photometry. It's basically just measuring how the stars dim with time and brighten with time. Although in this case, it's not because, unlike the Cepheid variable where the star itself was physically dimming and brightening, in this case it's because there's a planet coming in front and behind the star. Okay. And so because of this technique, which is a relatively new technique of using, where we use photometry, the Kepler Space Telescope has found over 2,000 planets around other stars. But this technique, we're still using it. Here's the TESS Space Telescope. And TESS was launched in 2018. And TESS has about a 400 times larger search area than Kepler. So it's going to do exoplanet detections in basically the same way, but it's estimated to find many more. What's exciting about TESS is that it's going to look for exoplanets that are closer to us. A lot of Kepler's exoplanets that are discovered are quite far, but TESS is going to look for some that are closer, including this system, which was just released this summer with a very nice name, GJ357. GJ357 is only 31 light years away from us. It's very close as far as star systems go. And TESS discovered this inner one, 357b, around this small little M-dwarf star. And TESS discovered that. And then once TESS discovered that, what happened was astronomers around the world decided that they would look back at all the archival data of that star from other ground-based telescopes going back all the way through the late 1990s. And they realized that they had, in that data, these two other exoplanets that had never been detected. It lived in that data, but they didn't know it, and they didn't know how to look for it until TESS found that first one there. These are all super-Earth size, so larger than Earth. That 357b is much too close to the star to be habitable, but you see this blue region called the habitable zone. 357d is potentially habitable. Follow-up missions will have to explore the habitability of that exoplanet. But it's about 6 times the mass of our Earth. It's called a super-Earth. Okay, so photometry is a very powerful tool that you can actually do yourself with this online tool called Do-It-Yourself Planet Search. What's really cool about this tool is that you yourself can do the same techniques that astronomers do, and you can discover exoplanets. Okay, and the way it works, and by the way, I know you're like, I'm never going to remember all these tools. I'll give you one URL at the end that you can find everything at, or one place you can look. The DIY Planet Search is a nice tool where you can basically do the same processes that astronomers do with photometry. So basically what you do is you first choose a target. There are many targets. You can choose these, and I should say these are known exoplanets, so you're going to get a result if you do it correctly. Okay? These are known exoplanets that we've discovered. So you're going to get a result. So if you want to do this, you can observe anytime. You can also go back in the past and observe. That's nice if you want something right now. You don't have to wait for it. I went ahead and did that because we aren't going to wait several days. And let me show you what I did. So I just want to bring this up so that you can see. Let me see, it's this one. Yeah. All right. So what you can do is you can bring up an image. So basically, you can observe the telescopes. This is the same micro-observatory telescopes, by the way, that I showed you earlier. Okay, they observe. They're just 6-inch ground-based telescopes, but they can still detect exoplanets, which is amazing. So if you hit View, you come up with a region of the night sky, and there's instructions on how to do this, but I'll just walk you through real quick. The first thing that any astronomer needs to do is to find their star. One of these stars has an exoplanet going around it. Which one is it? That one? You're right. You're right. Right. Well, right. It's the one with the yellow circle on it, right? Yes, that's it. So there's a finder chart, right? There's a finder chart here that lets you find your star. So the process is you first calibrate your image, and what that means is that you subtract off what's called the dark noise or the dark current from the chip. All these CCD chips have these interesting noise features. First thing you do is you subtract that off because that's just noise. So you click calibrate, it does it for you. And then you bring up your finder chart and you try to find out where it is. And you see these 2 stars there, look an awful lot like these 2 stars. If you ever observe it in the night sky, if you've ever done observing with your own telescope, you know the idea of star hopping, where you try to find the bright ones and you sort of hop around. And then the yellow one, which is that one, is our target star, right? So let me close that because I know what the answers are. All right, so basically you put your little cursor here and you click on this. And when you click on it, what it's doing is it's basically saying it's going to count up all the photons or all the light within that circle. That's what that circle is. It's like your bucket. It's going to count all the light in that circle. It asks for 2 comparison stars because we're looking for a star that varies with time, and you need to compare it with a star that doesn't vary with time to get sort of a relative measurement. So the finer chart tells you where these are, but I'll just click them here. There's a comparison. And then they just want you to click on a couple dark patches of sky because the dark sky could actually have some small amount of brightness that you might want to subtract off. Okay. All the instructions walk you through that, and then when you hit calculate and record, you are going to, it'll tell you, okay, relative brightness measurement. So it's about 80% as bright as the average of those 2 stars. What's important is you do this, as you can see with the check marks, with enough of those observations of that same star, and you graph the brightness. It'll graph it for you, and you can start to see, although it's noisy, you can start to see a trend where there's a dip, where in here is where the transiting planet must be in front of the star, right? Now, again, this is pretty powerful because this is only a 6-inch telescope. These are pretty small telescopes, but they're pretty powerful. The idea that with a 6-inch telescope you can actually discover a planet around another world is quite amazing. And in fact, if you go onto this tool, you will, there's opportunities to work with others in the community that use this tool to pool your answers together to get even more accurate data. So this is a fun tool that gets into photometry that we would happy for you to share with others. I want to also just make a couple other points about other tools. We work in a learning program called NASA's Universal Learning. This is a NASA program where Space Telescope is a member, but we have partners across the country, including at Sonoma State University. And they're leading this effort called the Global Telescope Network, where you can basically do what we just did with that, but with even larger telescopes, ground-based telescopes, and even do more. You can do exoplanets, just like we just did there, or you could do variable stars, like Henrietta Leavitt was doing and Edwin Hubble was doing. Okay? So there's online tools that you can do and learn about with the Global Telescope Network. Likewise, there's a project that's coming out very soon that we're excited to share with you. It's called the Exoplanet Transit Survey. This is aimed at amateur astronomers and smaller colleges, universities. Basically, you can observe high priority transiting exoplanets discovered by Kepler, TESS, and other surveys. This is getting more into doing this is really getting into actual science here. So the whole point of this is to pool together ground-based telescopes, small, large, whatever they are, and to do things like follow up on potential TESS discoveries. Okay? So TESS is going to do a lot of discoveries, but TESS is only going to maybe visit some of those, maybe one visit or one pass. So there might be uncertain. So if you follow up with these ground-based, you might actually be able to confirm that there's possibly an exoplanet there. Okay? And so this is something that's going to be out in the hopefully next several months. So keep that in mind. Again, this is a NASA's Universal Learning program. And this is done with our partners at NASA's Jet Propulsion Laboratory. I encourage you to, and I'll point this again at the end, go to NASA's Universal Learning site. All of the activities that I show you will be there. All right. Spectroscopy. Probably, I'm biased, but I think this is the most powerful tool in our toolkit. So how are we doing on time? We're just getting to the punchline. We all right? Okay, all right. All right, so spectroscopy, and you got a nice litho that showcases some spectroscopy. They say a picture is worth 1,000 words. Sometimes they say a spectrum is worth 1,000 pictures. Spectroscopy really has a lot of information in it. What is spectroscopy? Well, spectroscopy is just breaking up the light you get into the component colors. Okay? A lot of people credit Isaac Newton with sort of the invention of the field of spectroscopy, although others were doing spectroscopy before him in the 1600s. And in fact, the Romans were breaking up light with glass and seeing rainbows. But Isaac Newton, in his optics book that came out in 1704, basically put together the fact that you can actually break up white light into the component colors and put the component colors back together again in white light. So he basically showed with his experiments that white light was really comprised of those colors of the rainbow. All right, so you can see him with a prism there in that painting, breaking up the light. All right, so let's go ahead and do a demo. I have this up here. This is sort of an idea. There's a lot of stuff on here. All I want to get across is that in most cases on a telescope, if you're trying to take a spectrum of an object, if you're trying to break the light up of an object, you want to only get the target usually, right? So you have a star or you have a galaxy or something, and so you need some way of preventing all the other light from the image from getting into your this grating is essentially a prism. You only want your target to be broken up into a spectrum. That's not always the case. There are other spectrographs on our instruments, things like called IFUs and other things that you can basically get a spectrum of the entire field, if you will. But the idea is that you take the light from a source, you pass it through. In this case, it's a grating, but it acts like a prism. You break up, you bend the colors of light, and then you put it on a detector, your CCD chip, and you read it off. Yeah.
Who reviewed that diagram? Because you've got the red light going to the spectrum and the blue light going to the red end of the spectrum.
Yes.
I just want to point that out for the audience. Yes. That's a silly error.
Yeah. 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 It is. Just imagine that it's flopped. All right. All right. Theater of the mind, people. All right. Okay. Thank you, Frank. But what's powerful about spectroscopy? Why is spectroscopy so powerful? There's so many things you can learn about an object with a spectrum. Okay. You can learn. In this case, we're showing you one example. You can learn the composition of the object, what the object is made out of. You can learn how far away an object is. You can learn how fast it's moving through space. You can learn the temperature of an object. There's so many things that a spectrum can give you if you take a spectrum. So with that, let me go ahead and switch over. We're going to try something let's see if this works. All right, we're going to go ahead and do a demo here. And before we turn before we turn the lights off, I need to switch it over. See if you can see. I want you to see what I can see on my screen here. There we go. All right. Okay. All right. Now, what I have up here in the front is I have a camera with essentially a prism or a grating in it that's going to be our spectrograph. And then I have these tubes that are filled with an element. Okay? And I'm going to I'm going to turn this on, and it's going to heat the element, the gas in this, and it's going to give off very specific colors that are associated with that gas. Okay? Essentially, it's going to give off a spectrum. It's what we sometimes call a spectral fingerprint. So let me go ahead and turn that on. Okay, you can go ahead and turn the lights off now. Yeah, thank you, Thomas. All right, turn that on. All right, good. Okay, so when you look at this screen, all right, so there's the tube. You see it bright. That sort of hashed bar is essentially the amount where I want the light to come through. So I don't want to include all this other stuff in the spectrum. And then here's actually where it breaks it apart. And then you can see over here it graphs it for you. So these are nanometers. These are essentially the wavelength of light. And this is intensity, or how bright the light is. And you'll notice that a few lines really stick out. Okay? And those are the fingerprints that tell us what this element is. Does anyone know what's in this tube? How many chemistry spectroscopists do we have in the room? Argon. All right. Well, luckily, people have done this in the laboratory for a long time, and they have the answers for us. So let me go ahead and show you. I'm going to overplot a line here, hydrogen lines. And what you'll notice is these are called the hydrogen bomber lines, but they mark them. So this is called hydrogen alpha, hydrogen beta, and so on. There's one there. It turns out you don't really see these because the sensitivity, the chip drops off over in the violet end, so we don't really, the chip can't detect those colors. This is all noise over here, by the way, so you can ignore this. But here, between here and here, is essentially what the chip, somewhere around here is what the chip can see. So that tells us that we have hydrogen lines. So when an astronomer is doing this, and this is actually a lot of what I did for my PhD work, is we get a spectrum from an object, okay? And it's a mystery, right? And so you create these line lists like we have here. This is hydrogen Balmer. But you know, if I also clicked on H2O, water, that's what the water lines would be, or neon, or so on, right? You can see it gets quite complicated if your object has a lot of different elements in it, but that's where you make your money, right? All right, so that's hydrogen Balmer, but let's actually take let me turn that off for a second and let me overlay on here a reference star. I'm going to do, this is the spectrum of a star, an A0 star. This is basically, if you've heard of the star Vega, this is equivalent to Vega. What you'll notice, you notice that those, we call these emission lines. The hot gas from the tube is creating these emission lines, these spectral fingerprints. You'll notice that they overlap directly with these dips that you see in the star spectrum. Okay. It turns out that for stars, they have these outer atmospheres. Okay. So this hot gas is emitting these signature. Stars have these cooler atmospheres where they absorb the photons from specific elements. So this star has an outer atmosphere of hydrogen, and we know that because it's absorbing hydrogen because there's less hydrogen. That line is associated with hydrogen. And so we can actually use, these are called absorption lines. So whether they're being emitted from a hot gas like that tube, or whether the gas is absorbing photons, the gas is cooler and absorbing photons, you can still, doesn't matter if it's emission or absorption, you can determine that hydrogen is there, right? So this is actually one of the ways in which they did the stellar classifications of stars. So if you ever wondered why stars have these weird classifications of O, B, A, F, G, whatever, if you've ever heard of that, it actually initially came from using spectroscopy and looking at the strengths of the hydrogen Balmer lines. Some A stars have very strong hydrogen Balmer lines. They have very strong hydrogen present in the Balmer series. And I keep saying Balmer because there's different kinds of hydrogen lines. Let me go ahead and do another example. Let's go ahead and turn that off here. All right. Actually, let me go ahead and turn on. See, this is a star. This is a G2 5 star. So this is a star like our sun. So our sun has a spectrum like this. Our sun is a cooler star than the A star. And as you get cooler and cooler stars, you're going to notice that the spectrum looks a little messier. But it's actually because there's a lot more features that you see. Okay, so it gets actually quite complicated. It's hard to see, but there is hydrogen there. You can see that matches up with that, and there's hydrogen there. But there's something else that's really cool that I want to show you. Let's take hydrogen out. Let's put in a different element. All right, you can see this has a lot more lines, right? This spectrum is quite busier. But you'll notice that there are some features that do overlap with this sun-like star spectrum. Nominally, this sort of yellow line here, you kind of see a dip up there, and in fact, I could, if I see if I can make this work, I might be able to. I'm not sure. All right. There was some way, but I forgot how, of zooming in. Anyway, look at the mouse. Look at the mouse. It'll tell you where it is. All right. So there is a dip there, and it turns out that, does anyone know what's at around 588 nanometers? What was it? Not sodium, although that color looks very similar to. It's actually helium. This is a helium spectrum. And it turns out that this is how helium was discovered, because helium is very rare on the Earth. It's a very light gas. Helium was first discovered in the sun. And this was the line that we discovered helium, this 588 nanometer line. So using spectroscopy, we're doing a lot of things, but we're also, filling in the periodic table. And that was actually done in, let me see if I have that date. Yeah, 1868. All right. So, let's see. We could play with this all day, but it's getting late. But actually, if you're interested after we're done, if you want to come up and take a look at it too, I'm happy to show you this or any of the other tools. All right, so let's go ahead and, I'm going to go ahead and go through a few more things, and then we'll wrap up. All right, I have to do this again. Look at my dust. Yes, it's the best. All right, okay. All right, so this is what I studied as a graduate student, and this is something called the diffuse interstellar bands. There's probably 10 people in the world that study this. I'm only slightly exaggerating. But it's a very difficult mystery. This is a sort of a more modern day absorption profile look of it. Each of those dips are absorption features that are called the diffuse interstellar bands. They were first discovered around 1919 by Mary Leah Hager. She was a graduate student at Lick Observatory. And they're the longest spectroscopic mystery in astronomy. We don't know what these are. These are absorption features from things that we can identify in the interstellar medium. So we know it's coming from the space in between stars because of the way the features look. They don't look like they're coming from around stars. They don't have the sort of spectrum that you would expect if they were near a star. They look like they're from the space between stars, but we don't know what they are. Okay. So it's been a mystery, and there's actually over 400 of these absorption profiles now that we don't know. When Mary Leah Hager discovered them, I believe she discovered 2 of them initially, and now we know of over 400. And they're throughout the visible part of the spectrum and close into the near infrared. Near infrared's here, visible spectrum's here. So that the kind of light that our eyes can see. All right. So it's a big mystery, but we have made a little bit of headway in the last year. After all this time, we discovered what a few of them are, and they are buckyballs. They are these things called buckyballs. Buckyballs are really interesting. They're these organic molecules, these carbon and hydrogen molecules. These are sort of carbon rings that fold over to make these balls that you see here. And they're quite sturdy. This is a video I can play, actually. Let's see if it plays. Yeah, let's see if I can do it. Anyway, there's some text there because I grabbed it from the JPL site. But now this isn't the first time that we've discovered buckyballs. Buckyballs were discovered in space in 2010 from the Spitzer Space Telescope. They found it from a star that's been dying, a planetary nebula. And that was really interesting and cool. But the thing about planetary nebula is that there's a lot of awesome dust there that shields these molecules and prevents them from being torn apart from the harsh radiation of interstellar space from all these other stars. So we could explain that. Okay, that makes sense. These dying stars produce this soot, these buckyballs, this carbonaceous material, and they're protected in this planetary nebula phase. But what's interesting about this discovery from Hubble just this year is that some of these buckyballs are actually in interstellar space, where we expected the harsh radiation in interstellar space to tear them apart. But they seem to be hardy enough to survive. And in fact, if they're that hardy, and in fact, a common belief, or a common hypothesis, I should say, for what a lot of the diffuse interstellar bands are sort of these carbonaceous grains. They're molecules, not grains. These carbonaceous molecules. If that's true, it tells us something about the habitability of our universe, because they are quite common. They're quite ubiquitous. And carbon and organic molecules that carry carbon are what we think are the precursors to what we need for the prebiotic molecules that would later then form life. So the idea that the interstellar medium, that our galaxy could be filled with these carbonaceous molecules, potentially even raining down on the early Earth, might be a source for how we got the ingredients in the early days of the Earth, from when who knows, magic happens. Nobody knows exactly how life got started, but chemically. But you have some material there, and life happens somehow. So this is a big part of that mystery. And then I want to close by saying something about the future. So spectroscopy spectroscopy is going to be a big part of our future, and the James Webb Space Telescope, which I'm sure you're all aware launches in a couple of years, is going to be a spectroscopy machine. It is going to do so much with spectroscopy that it's actually going to be hard maybe to even handle all that amount of data. So it has several spectrographs on it, but I want to highlight one of the most interesting ones. This is an instrument called NIRSpec, and it's a new technology for collecting spectra. Basically, what happens with NIRSpec is you have these little shutters, okay, on the camera, and by the process of using a magnet and electric charge, they can open and close these individual shutters, which are very tiny. We're talking about smaller than your hair, like these little shutters, which are very tiny, and they can open up, and you can choose which objects on whatever field you want to take a spectrum of. So whatever's open, you'll get a spectrum of that. Okay? So instead of the current model where we have to carefully pick one object in the field, which is the most common case, one object in the field and we get a spectrum of it. It's very it's very laborious, it's very time intensive. We can just open the shutters and just get a flood of spectra, high resolution, medium resolution, really high quality spectra from the universe. And so this is really going to change the game for our understanding of galaxy evolution and all sorts of things. All right. And then I'm going to fly through these last bits quickly, but I feel like when you talk about tools in astronomy, you cannot not talk about these last few slides. These are also the area where, in many cases, I am the least of an expert. There's not a lot of dust here, but I do want to give it its due. This is an amazing era of astronomy that we live in. This multi-messenger astronomy. And what do I mean by multi-messenger? It's an interesting name that astronomers have given this field. The idea that the universe is sending us messages in a bottle, if you will. But multi-messenger is essentially everything that I talked about was using light. Okay? As astronomers, unless we are lucky enough to be a planetary astronomer, we can't go to the places that we study and take samples of these objects, right? They're too far away. All we have to study are what the universe sends to us, right? The messages that it sends to us, right? And so for the longest time, right, we've used light, started with visible light, then we moved across all of the types of light. But there are other ways that the universe can give us information, okay? So let's go through those. So of course, we already talked about light, and so I won't spend any time on this, but light is the way that we've been studying the universe the most. But there's also particles. There's also matter, mass, okay? Charged particles, small things called neutrinos. These are things that come from high energy events in the universe that send us that get sent throughout the universe, and if we're lucky, we can capture them. This image here is of a tank underground called Super Kamiokande. It's in Japan, and it gets filled with 50,000 tons of purified water, and it has over 10,000 light sensors. And basically, this entire purpose of this tank, this observatory, this telescope, for lack of a better word, is to detect some of the smallest particles we could ever think of, called neutrinos. And there are thousands of neutrinos coming through our body every second. They're so small they don't interact with matter at all. Okay? And they come from things like the sun and high energy events and so on. But if we can actually start detecting these, which we have, we've started to be able to detect these neutrinos, it'll give us insights into things like what's happening in the center of the sun that we can't see with light. Okay? So that's a very powerful tool. And then there's also gravitational wave astronomy. If you've been alive the last couple of years, you probably have heard of gravitational wave astronomy. This was a big deal. These gravitational wave detectors, you see the two here from LIGO, one in Washington State and the other one in Louisiana, I think, Louisiana. And essentially, the idea is that if you have these really massive objects like black holes or neutron stars collide, they'll send ripples through space-time. And those ripples will come and they'll interact with the Earth. That's a highly exaggerated way of interacting, by the way. It's not quite that bad. But they'll interact with the Earth. And as space-time itself increases and expands, okay, it'll pull these different lever arms. And there's lasers going through these that estimate the distance. And they'll be able to tell the wiggling of the Earth as a gravitational wave goes through. And the fact that you have two of them gives you some hope that you actually might be able to pinpoint roughly the source on the sky where they came from. Okay? Because one might hit this detector first before it hits the other detector and so on. You might be able to triangulate a little bit. And so actually we've been able to do that. And so LIGO now has discovered with the gravitational wave detectors these merging black holes. And what's really interesting is, so the blue here are all the gravitational wave detections. The purple here were detected by some signature of light coming from the merger. But with the gravitational wave, we're probing larger black holes than we were able to probe before, okay, and learning more about them. And you can also do the same for neutron stars. So this is a neutron star detection. So neutron stars are the dense cores of old stars. And Frank's getting up, which tells me
You got 10 minutes left, and you're not going to get any questions in unless you finished up.
Yep. All right. Well, this is my last slide. Okay. Nice time. All right. I also have to say something about tools. There's a whole field in theory and modeling. Every subject of astronomy and astrophysics has theorists and has modelers that work on understanding the basic physical concepts. And I just want to play this because it's beautiful. This is an illustrious simulation. This is essentially putting in the physics of our known universe into this really powerful computer simulation and watching it play with time. This purple here, this is basically looking at our 10 megaparsec view of our universe, and you're seeing dark matter here, and you're seeing all the gravity that's condensing these proto-galaxies together, and when they start to merge, you see these filaments, and when these galaxies start to merge, there's star formation happening, and then you're going to start seeing stars blowing up in supernovae and giving their gas back out into the material between galaxies, the intergalactic medium, so you can start seeing some stars going off. By doing something like this, we put our understanding of the physics into these computer models, and then we compare what we see in here with our observations. And if they don't match up, it tells us that either we're doing bad observations, which I never believed, or that there's some fundamental misunderstanding of the physics that we need to resolve. Okay, so that's a huge area. So with that, I'm just going to leave up the Universal Learning URL where you can get all of our activities, and I'll leave it open for questions.
All right. All right, we just have a short amount of time for questions. What?
So I have one that I saw in the chat online, which is, what is an absorption feature?
Yeah. So an absorption feature is basically you have all these photons going around, and as if a photon of that particular, of a light of that particular color, say that yellow color I showed you from helium, if a photon that has that particular color interacts with cooler gas made of helium, it's going to get absorbed. Okay. So then you're going to see an absorption feature is essentially a dip in the amount of light that you see. So you have the starlight in the example I showed, and it's bright, and then there'll be a dip because that photon that was trying to reach us, that basically got stopped. Okay, it couldn't reach us.
So you're telling what's there by telling what's not there.
Yeah,
Okay.
yeah. That's an interesting way to put it. Yeah.
Questions? Oh, all the way in the back.
Hold up.
Oh, we have a microphone. Wait for the microphone so the online audience can hear. There you go.
Hello. I've heard a lot of talk today about the different telescopes that we've been putting out in space, and they all kind of observe, sort of passively, as it were, all the electromagnetic radiation from the universe. I'm wondering, are there any other devices out there? Like I remember the Magellan mission used synthetic aperture radar. Is there any other synthetic aperture radar that uses active detections right now or in the future?
Now, when you mean active detections...
So maybe transmitting something to receive something back.
I see. Well, the distances in the universe are so vast
Certainly.
that, you know, I know the SETI project sent a message with radio, but in
I haven't
terms
heard anything back from that one.
yeah, we haven't heard anything back.
We have used laser off the moon
Yeah.
and radar off Venus.
Right.
Okay.
Yeah.
Any others like that on the other planets?
I'm not sure if there's been any other from the planets. Yeah, I mean that's the only hope you have though is see I generally forget that we have the solar system, so
Right.
that's
Yeah.
that you reminded me
There
about
is
that.
some dust in the solar system.
There is
okay?
some. There is some.
You just
dust in
don't
the
love
solar
it.
system. Yes. But no, that's a good point. So that is another way of getting information from objects in the solar system. Yeah.
Thank you.
Yeah. Oh wait, Grant, we gotta.
Okay.
We have an online audience that needs to hear your wonderful question.
Yeah.
It won't make it to the microphones.
Yeah, unless you can shout to Antarctica.
We don't.
What,
He was joking.
what you call dust must be incredibly variable throughout the universe.
Yeah.
But what's it like?
What's dust like?
It obviously becomes dense enough to become a star, but it just dust. You know, we think of dust as what we think of as dust.
Yeah. Yeah.
This
Dust bunnies
must
under here.
be-
Yeah.
If you're in it, I mean, am I like in it, or is it so far apart each particle that I don't even know that
It's
I'm in it?
quite far apart, but the studying of the composition of dust itself and the sizes of dust is its own field. So dust comes in a range of sizes, and the actual breakdown of where you go from being molecules to being a dust grain is not exactly defined. It's physical properties that define that, but you know, you start out with molecules, and if you get large enough where the molecules stick to dust grains, you can start to grow them. Dust grains can stick together, you can start to grow things. Of course, things can tear apart dust grains. It's this active process. And compositionally, there's lots of different kinds of dust. There's carbonaceous dust, there's silicate dust, there's ices out there, so sometimes dust is covered in ice. And chemically, that produces a lot of different possibilities for what you can actually create, the types of molecules and things you can actually create. So a lot of things are actually created on the surface of dust grains themselves.
So, like, what's the average density of an interstellar dust cloud? Because, you know, the air we're breathing now is billions and trillions of particles per cubic centimeter.
Well, certainly much less than that. I don't
I know.
know. Yeah,
It's like 10 to the 5th
yeah.
particles per cubic centimeter.
I don't actually recall the actual density of it, but it's yeah.
So, I mean, even the dust clouds that he's talking about are way lower density than the air you're breathing right now. Okay.
Yeah. Well, and the thing is there's also a range of densities of dust clouds too, right? So So I mean, we have things like some of the nebula that you look here, but then there's also dust clouds that are much denser. That in fact we typically wouldn't use Hubble to go observe. We would only see them in shadow anyway if we do observe them. They have interesting names like Bok globules and things, but they're the places where we think the stars are actually forming in, and those are where you have the densest places. The densest amount of dust is in those regions.
Okay, you have an online question. Do neutrinos pass through the entire Earth without hitting anything because solid matter is mostly empty space, or because neutrinos don't interact?
Good question.
Isn't that-
That is a good question. That is a good question. Yeah. Remember when I put up multi-messenger and I said that I am not an expert
I'm
in
not a
multi-messengers?
neutrino.
Yeah.
I think
It might be both, right? I mean,
it's sort of both, but I mean, if you just think about the normal interaction of a photon with things versus a neutrino with things, they're really low mass objects anyways, both of them, right?
Right.
And so I would say it's just because neutrinos just don't interact more, would be more, because you're comparing it against something else that also.
Yeah,
would
that's a
pass
great
empty
question.
space.
Now I'm gonna do my homework.
Yeah, and they aren't electrically charged, so there's
Right.
very, very little chance for them to act as well. All right, over here.
Hey, this is the best astronomy lecture I've been to this month.
Thank you. Thank you. This month, all right. Well, I got
It's all right. It's only the third of the month, so
this month. Yeah.
Well, my
I got your
question,
$5 later,
and I
Brad.
just read this recently, the dust is so scattered, at least in the solar system, that a spacecraft, an average spacecraft, would encounter a dust particle every 3 days. Does that sound about right?
Yeah, I could believe that. Sure. I mean it's not dense at all. I mean, you're not. Yeah. This is the exact sort of thing that they have to think about when they create when they're building the spacecraft. Like for example, James Webb, they're gonna park it at the Lagrange 2 point 1 million miles away. They have to have they have some estimates of the wear and tear on the spacecraft over time as it interacts with dust grains or other small particles that are going through. So yeah, it's certainly not a bad enough issue that they're worried about it, ending a mission in a very short time frame. So it's not very dense. Yeah. But also space is very big. So if you actually were to add up all that material over all of that space, it amounts for quite a bit in terms of bulk. It actually adds up to a lot if you include it's scattered throughout the interstellar medium and throughout the solar system. So
Okay, thank you.
Back to the neutrino question. If neutrinos don't interact or don't bump into anything, how then do we detect them? For example, at Cameo, I don't know the pronunciation there, or Ice Cube, how do we detect them?
that's a great question. So they don't interact much, but if one in 100 billion or whatever, I don't know what the exact ratio is, and does interact, there is a very small chance that it will actually impact a water molecule. And when that does, it's a very rare event. They have those detectors there to see the flash. So it's incredibly rare, but it does happen enough that they've been able to detect some.
So it's a scintillation, very, very inefficient.
Yeah.
Right. So the
gotcha.
statistic I remember from graduate school way back when was that the original neutrino detector was a swimming pool of carbon tetrachloride, cleaning fluid, okay? So take a swimming pool of cleaning fluid, okay, shield it from all other radiation, and the neutrinos that are passing through it, you get about one interaction per day with a swimming pool of clean fluid, because the neutrinos would interact with the chlorine, create the Cherenkov radiation, and then the photomultipliers would be able to detect it. That was the original one. This is the super Kamikaze is much more advanced. All right, I think we have one more question. Who would like the last question here? All right, there we go. Go ahead.
So there's been in the news recently about the mega constellations of satellites and whatnot. How's that going to affect things? Is there a fight brewing? Can you subtract that out? Or
It's a very good question. I don't want to get on anyone's bad side if they watch this on the internet. Yeah, it is actually a problem. I mean, these satellites are a problem. I know, we do want, of course, 5G, and we want all the technology that comes with it. But, it essentially becomes next to impossible if you get enough of them up there, like what happened if they just happen across your field of view, to actually subtract it out. It kind of just, unless you happen to get your targets like in between them. So it's very disruptive. So who knows, maybe they'll feel guilty enough that they'll fund space telescopes more and put them up. So.
All right, it's 9:30, and I always cut off at 9:30, and Brandon has given you a ton of things to look about, to think about. All right, do we have our Maryland Space Grant Observatory person? Yes, all right. Is this Jacob or Alex? Jacob. Jacob's going to come down here over to my right. If you would like to go across the street to look through the telescope with Jacob, please come down and join him. Otherwise, we will see you next month. Thank you all for coming in. Good night.